Hello everyone, and welcome to Biopedia. In episode 90 of the podcast, we discussed how tall trees might be able to grow on the planet Mars. However, there is more to explore within the topic of Mars itself. As evidenced by several papers which I'll list in the description, there is interest, or at least discussion, surrounding permanent colonization of Mars. Obviously, this comes with certain difficulties. However, I wanted to focus on one particular angle today, which also ties in quite nicely to some past episodes and some which I have, at least speculatively, planned out for the future. The issue we're going to deal with today is how we measure time on the red planet. We previously reframed Earth's history in terms of galactic cycles in episodes 71 and 94. Well, today, let's explore how one particular paper thinks we would go about solving the quandary of Martian timekeeping. Fundamentally, what we need to consider is that Mars has a different orbit to that of Earth and spins on its axis differently. A Martian day, or a sol, is 24.6 hours long, compared to 23.9 hours for an Earth day. This sol, by the way, is an abbreviation of the phrase solar day. Then we get the complexity of a Martian year. This is 669.6 sols in duration. If we convert this into Earth days, the Martian year lasts about 687 Earth days. So, as you can see, the Martian year and day have a different makeup to that of Earth. This presents the main problem in creating our new Martian calendar. However, we have a paper from 1997 which takes us through the steps. First up, we have to discuss the idea of leap years. Our Gregorian calendar in the modern day has what's known as a two-parametric leap rule. What does that mean? Well, to answer this, we have to get into what leap years are and why they exist. We perceive our Earth year as being 365 days long. However, it isn't that neat. In actual fact, the Earth takes 365.242199 days to go around the Sun. Fairly obviously, if you have a system which makes a year 365 days long, or 365.25 days long as the old Julian calendar did, you're going to get a discrepancy and hence calendar drift. The Gregorian calendar was created to account for this difference in the 16th century. So, here's the leap year system. Every 4 years, we add an extra day onto the year, as the old Julian calendar did, creating 365.25 days in the year on average. However, we still have a bit of difference to account for. So, every century, so think the years 2000, 2100, 2200, etc., is not a leap year. But then, extra step, every year which is divisible by 400, like 1600, 2000 and 2400, is a leap year again. So, there are two different rules for which years are leap years nestled within each other. Hence, it's a two-parametric leap rule. We have two parameters to determine which years are leap years. The author behind the 1997 paper, Joseph Suran, came up with a Martian calendar which has 3 such parameters. In addition, he doesn't use a leap year. Instead, he uses skip years. Basically, every so often, the calendar misses out the last week of the year. If you're missing out 7 days in order to compensate for calendar inaccuracies, this would obviously happen less often than needing to add a day would do. So, here's the system he came up with. A skip week is used rather than a leap day. Years which are even are skip years. This is the first step. So, year 2, for example, would miss out the last week of the year, as would year 4, year 6, and so on. However, years which are even, but also multiples of 70, are not skip years. The extra rule goes that any year coming after a multiple of 1100 would also be a skip year. This is, for example, 1101, 2201, 3301, etc. They all come one after a multiple of 1100. We'll put this into practice with an example timeline at the end of the episode. The question is, how accurate would this make the calendar's constructed reality compared to the actual Martian orbit? Well, according to the author, there would be an error of a day in a period greater than 100,000 years. By comparison, it's estimated that another day, let's say February 30th, will need to be added to the Gregorian calendar in about 3,300 years. With that said, let's get to what the actual calendar is meant to be. The Suran calendar, as I'm going to call it, without any skip weeks, so the full complement of time in a year, consists of 672 Martian sols. Rather satisfyingly, these are divided into exactly 24 months of 28 days. Now, remember, Mars' orbit takes 687 Earth days, which is close to 2 years. If the year is a skip year, the last week of this year would be taken off. Speaking of which, the calendar is, like on Earth, meant to divide into weeks of 7 days. Given that each month is 28 days, this would leave you with a year of 96 weeks. Okay, so we've got the days, the weeks and the months, but what do we call any of these? Well, Suran took pains to ensure that his calendar could adapt Earth-like terminology. So, each 24-month year is split into 12 bi-months, meaning that Terran months could essentially be transferred across with a bit of modification. As an example, the first month in this system is named Januarione, with the second half of the bi-month being January-ide. The second bi-month is split into Februarione and February-ide, and so on. Alternatively, as Mars has 2 moons, you could have the January of Phobos and the January of Deimos, etc. This then keeps going until you get to the end of the year. As for days of the week, they're kept largely the same, but the suffix changes according to the idea Suran lays out. So instead of our usual days of the week, you have Mondim, Tuesdim, Wednesdim, Thursdim, Fridim, Saturdim, and Sundim. I'll bet this all sounds a little bit abstract, so let's put all of this together into an example timeline. Bear in mind that this example is going to be with the heavy caveat of this is provided I've understood all of this correctly, as going through calendar-based papers is not my usual fare. So, the Martian Society gets founded on Mondim the 1st of Januarione, Year 1. Year 1 has the full complement of 672 sols or Martian days, divided into 24 months of 28 days each. Year 2 would then be a skip year, as per the first rule we've laid out, so Decemberide would have 3 weeks rather than 4. Therefore, Year 2 would have 665 days, divided into 95 weeks rather than 96. Year 3 is then a non-skip year, Year 4 a regular year, and so on. We then get to Martian Year 70. Normally, this would be a skip year because it's an even-numbered year. However, it is fairly obviously also a multiple of 70, so it's a normal year with 672 days and the full complement of 96 weeks. The same then goes for Year 140, Year 210, and so on. The next change comes in Year 1101. This is an odd-numbered year, so it would not normally be a skip year. However, our third rule in the 3-parameter skip year system means it is in fact a skip year. So, hopefully that's the hypothetical Martian calendar straightened out. Now for a final interesting question. Let's say that, as per one example mission timeline which NASA has on its website, Mars is colonised in 2039, and let's say January 1st to make it easier. What would the year then be on Earth when we reach the Martian year 1102, completing this cycle we've been talking about? Well, multiplying 1101 complete Martian years which have passed by 687 Earth days per year gets us to 756,387 days having passed between the settlement of Mars and the 1st of Januarione 1102. Dividing down again by 365.242199 for Earth days in a year, we get 2070.92 years when rounded to 2 decimal places. This decimal means that, roughly speaking, we would have completed 2070 years and would have 29 days left of the 2071st Earth year. So, taking all of that into consideration, January 1st, 1102 of the Martian calendar would be early December 4110 CE. Quite remarkable. So, that brings us to the end of today's episode. Thank you for listening, and I hope that any hypothetical future Martian astronauts enjoyed it and found it useful. That also brings us to the end of 2025, so thank you again for listening. If you have any questions or comments, or topic suggestions for future episodes, feel free to get in touch with the show's email address. Until next time, have a great week, everyone.